Let's consider the question of finding all the second partial derivatives of v, which is equal to e to the power of x e to the y, right? Second partial derivatives, much like second ordinary derivatives, you first take the first derivative and then you take the derivative again. Finding all of the second partial derivatives will require us to have both of the first partial derivatives. So let's find those first, and then we'll move on to the second partials afterwards. Let's find what we can write as v sub x, or the partial of v with respect to x. You don't need to write both of these. I'm just demonstrating the notation. You can use whichever you prefer. In most cases, sometimes one is a bit more necessary, but they are generally interchangeable. So we look at this expression and we take the derivative of this with respect to x. So we have an exponential function that is its own derivative. So we have e to the power of x times e to the y. Multiplying by the chain rule, we have to multiply by the derivative of what's inside. Now, we're differentiating with respect to x, which means we're holding y to be constant. So e to the y is constant. So the derivative of x times e to the y, the derivative of x is just 1, we're left with the e to the y. So we have that. If we want, we can combine those together and make that e to the power of x e to the y plus y, all in that exponent. It's unclear at this moment which of those would be simpler for our purposes, but those are both possibilities. So there's our partial with respect to x. Let's take the partial with respect to y, v sub y, or the partial derivative of v with respect to y, using the Leibniz notation here. Again, this is an exponential function, so we start off with ex to the ey, and now we multiply by the derivative of that exponent. I just did the fraction problem. My head's stuck on fractions. Now x is constant and y is variable. So we have the derivative of x times e to the y. Well, x is constant, so we still have the x, and the derivative of e to the y is e to the y. So we have that. And if we simplify that a little bit, we get x times e to the, again, we can add this exponents there to get x e to the y plus y. Okay. So those are the first partial derivatives. The second partial derivatives are what we would get if we take the derivatives of those. So let's do the pure partials first, and then tackle the mixed partials afterward. V sub xx, that is the second partial of v with respect to x, is what we get if we take v sub x, which is this last expression here, and take its partial with respect to x. Well, we have an exponential function. That doesn't change. We have e to the power of x e to the y plus y. And then the chain rule says we have to multiply by the derivative of what's inside of that. So the exponent, in other words. Y is constant with respect to x, so that part will go to 0. We have x e to the y. Derivative of x is 1. Again, e to the y is constant. So we again are just multiplying that by e to the y. And if you want, you can simplify that. Again, we're multiplying two exponential expressions with the same base, so we can add the exponents, and that gives us e to the power of x e to the y plus 2y. The other pure partial derivative would be v sub y, and that is the second partial of v with respect to y. Now we look at v sub y, this one right here, and take its partial with respect to y. It's starting with an x, that's constant. It's a constant factor, so we can leave it alone. That's multiplied by an exponential function. So we have that natural exponential function itself, e to the power of x e to the y plus y times the derivative of what's inside, so that exponent. Now you'll note that both terms of the exponent depend on y, so we'll have two terms here. The derivative of x e to the y with respect to y is x e to the y, because x is constant, and the derivative of e to the y is e to the y. Now we have plus the derivative of y. The derivative of y is 1. So we have that expression there. If you want, you could multiply that out, but I think that just sort of makes it messier in this case. I wouldn't really bother with it. So that's fine how it is. Now, those are the pure partials. We can also take the mixed partials. So let's look at v sub xy. This means that we take v sub x, the partial with respect to x, and then take the derivative of that with respect to y. That can be written as the second partial of v. We're taking the partial with respect to y of the partial with respect to x. So note the order switches between the subscript notation and the Leibniz notation. Right? Because if you think about these subscripts, we're going from left to right. V sub x, x, v sub y, y, v sub x, y. Right? We're just following that sequence. Whereas this Leibniz notation is based on applying that partial differentiation operator, like partial by x, for instance, to some function. And then if you have another one of those, that can be stacked before it. It goes from right to left, right? So the orders are different. Be careful of that. Now, so this means we look at v sub x, which was this first one we had here, and now we are taking the partial of that with respect to y. Well, again, that's a natural exponential, so we copy that, e to the power of x e to the y plus y. We need to take the derivative of the exponent, the thing inside, by the chain rule. As with the previous one we did, again, both terms depend on y. And actually, we just sort of did that. This is going to work out the same way. We're taking the partial of x e to the y plus y with respect to y, which again gives us x e to the y plus 1. Now you'll notice this is slightly different from v sub y, because there's a factor of x here that we don't have in this case. Okay. So that was taking v sub xy. Now let's evaluate the other mixed partial. It's a funky looking v. Let's try that again. There we go. V sub yx. That is the second partial of v, and we're taking the partial by x of the partial by y. Again, it's the reverse order there. So this means we look at v sub y, this one that we have over here, and take its partial derivative with respect to x. Now this is the first time here we've had to apply the product rule in this problem, because you see we have a product of two things. We have an x times a function that depends on x. So let's take the derivative of the first factor first. Well, the derivative of x with respect to x is just 1. So we have 1 times this other stuff. So we'll multiply that. We have e to the power of x e to the y plus y, plus, by the product rule, now we will leave the x alone and take the derivative of the second factor. Well, that's an exponential, so that is its own thing, e to the power of x e to the y plus y, times, by the chain rule, the derivative of what's inside of that. We're taking the partial by x, so we have the x, taking the partial by x, so the derivative of x is 1. We have the e to the y, that's what's left, because that's constant, plus y, which is constant, the derivative of the constant is 0. So we have that expression there. Now, these two things look different, but if you distribute and maybe simplify a little bit as necessary, you'll discover that they're actually the same thing. They're just written differently. They're algebraically equivalent. I suggest you try that on your own to confirm it. Make sure you do get those being equal. But we find that v sub xy is equal to v sub yx. We took two different paths, and we got different expressions, but they turn out to be algebraically equivalent if we shuffle things around. This is not a coincidence. This is an illustration of Clairaut's theorem. I'm not pronouncing that correctly because it's French, but that's why there's silent letters in there. Clairaut's theorem basically tells us that if a function has, if all of the second partial derivatives of a function are continuous, then the mixed partials must be equal. And now there is a condition there, right? So we don't want to apply that willy-nilly. But this can often be useful. This is frequently useful. There are several times throughout this course where we will see that come in handy. So this does mean a couple of things, but with some caveats. One is that, I've mentioned that we want to be very careful about the order in which we differentiate. If we know that the derivatives will all be continuous, we don't have to be quite as careful because Clairaut's theorem allows us to take whichever order we want. We'll get the same results in the end. So if you're asked for a particular mixed partial derivative and you would rather take the derivative in a different order for whatever reason, maybe the structure of the function, you can see that, oh, if I do this first, that simplifies, maybe that term goes to 0, whatever. You can do that as long as the structure of the function is such that you can be sure that the derivatives are continuous. However, if you are asked to evaluate a partial derivative in a particular order, and you do choose to do that in a different order, make sure you cite Clairaut's theorem by name, because you want to make it very clear to anybody grading your work that you are doing this intentionally. If you take the derivatives in a different order and don't mention Clairaut, then it looks like you just didn't understand the notation and have accidentally taken the derivatives in the wrong order. So don't do that. Be very thorough to document your approach. You can use Clairaut whenever it's appropriate, but make sure you think for a moment that it is appropriate. And if you do use it, mention Clairaut by name. If you don't need to use Clairaut, just don't, right? Take things in the order given and work these out directly. But that's how second partials work. Given this, you can see how we can extend this to third, fourth, fifth order partial derivatives. In practice, we don't usually run into those. We rarely need to go more than second for most purposes. But that is how this would go in principle.